Hello and welcome to more matrices. We're going to start today with a little bit of a warm-up. And the first question I'm going to ask you to work on is multiplying this 2 by 2 matrix by this 2 by 1 variable matrix. It is possible because if you look at it, you can see that 2 rows, 2 columns being multiplied by 2 rows, 1 column, that since these are the same, number of columns here, number of rows here, those are the same, that we do know that our final matrix is going to be a 2 by 1 matrix. So go ahead and give yourself the 2 by 1 matrix skeleton, 2 rows, 1 column. I'm going to get a number there and a number there, and see if you can figure out what this product looks like. And I will tell you that both this spot and that spot will have an X and a Y in it. So put me on pause and take a few minutes to take a crack at it. Okay, so in order to multiply these two matrices together, first element here by the first element there, so 5 times x, plus second element times second element, so plus negative 7 times y. I'm just writing it as subtraction, as 5x minus 7y. And notice that this is just one term, well, not one term, but one element, 5x minus 7y. It happens to be a binomial, but it is just one element. This is still just one column. For the second row, first column, 3 times x plus negative 8 times y, 3x minus 8y. So now we're going to go ahead and use that and look at problem number 2. Can you multiply these together and then solve? Because what ends up happening is I multiply these two together, and notice that we just did that right there. So I end up with 5x minus 7y and 3x minus 8y. And this is a 2 by 1 matrix, and that's going to equal this, what is that doing there? That's going to equal this 2 by 1 matrix, which is negative 71, negative 73. So your instincts are probably right on, telling you that, well, if this 2 by 1 matrix is equal to this 2 by 1 matrix, well then 5x minus 7y probably equals negative 71, and 3x minus 8y equals negative 73. Take a minute or two and see if you can solve this system of equations. Okay, I'm not sure what method you used. I personally went to my calculator and did RREF, and based on what my calculator told me, what's all that? Based on what my calculator told me, I get x equals negative 3 and y equals 8. So x equals negative 3 and y equals 8. All right, moving on. Okay, section 13.5, chapter 13, section 5, we are working on inverses of matrices, the inverse of a matrix. And let's start out with somewhat of a warm-up. Here's matrix A, capital letter A. Here's matrix B, capital letter B. And here's matrix C, capital letter C. And right here I'm asking us to find A times B, B times A times C, and C times A. And what we'll know eventually, I don't want you to know just yet. So let me move this down a little bit. Extend page, move it down. We're going to need a little bit of room to work here anyway. So let me move that down, come back up. Now let's go ahead and start working on this. Okay, matrix A times B. So 2, 7, 1, 4 multiplied by matrix B, which is 1, 0, 0, 1. If I'm going to multiply this together, 2 by 2 multiplied by 2 by 2, it's possible. I'm going to end up with a 2 by 2, and then I'll put my final answer right here. This is for work over here, so let me get a better color. 2 times 1 is 2, plus 7 times 0, which is 0. Over here, first row, second column, first row, second column. 2 times 0 plus 7 times 1. Down here, second row, first column, second row, first column, 1 times 1 plus 4 times 0. And then right here, second row, second column, second row, second column, 1 times 0 plus 4 times 1. So I end up with 2, 7, 1, 4. Same as that. Interesting. All right, so that was A times B. Let's do B times A, B times A. And if you remember, matrix multiplication is not commutative. We can't immediately say that A times B is going to be the same as B times A because matrix multiplication is not necessarily commutative. Let's see if we have a special case here. So let's do 1, 0, 0, 1. And I'm going to multiply that by 2, 7, 1, 4. I'm going to get a 2 by 2 matrix. And let's see what it looks like. All right, let's go green. 1 times 2 is 2 plus 0 times 1. 1 times 7 is 7 plus 0 times 4. 0 times 2 is 0 plus 1 times 1. And 0 times 7 is 0 plus 1 times 4. And let's see what happens. 2, 7, 1, 4. Hey, look at that. This is a special case. Multiplication for matrices is not commutative unless one of the matrices looks like this, 1, 0, 0, 1, where you have the 1s on the diagonal. Try A times C and C times A and see what happens. Maybe you can make a hypothesis before you begin. Maybe your hypothesis would be if I multiply, A times C. That's interesting. What's going to happen when I multiply A times C? It's not using matrix B, so I don't think we're going to end up with the same as what we started with. Do A times C and C times A and check back with me in just a few minutes. Okay, hopefully I gave you enough time, or you took enough time. When multiplying matrix A times matrix C, you get the 1, 0, 0, 1 matrix, and when you multiply C times A, it turns out to be the same thing. 1, 0, 0, 1. 1's on the diagonal. And when you see a square matrix where you have the 1's on the diagonal and 0's everywhere else, that's known as the identity matrix. Matrix. For any square matrix, same number of rows as columns. For any square matrix, same number of rows as columns. A and I, where matrix A is any matrix, matrix I is specifically the identity matrix. So any matrix times the identity matrix is commutative, and it's just going to give you back the original matrix. And we saw that up here. Here's A, here's the identity, and notice it equaled A. Here's the identity multiplied by the original, and notice it equaled the original. So, special property of that kind of matrix, and we're going to talk about that. A little review of something that you've done back in middle school, probably, some basic vocabulary and concepts. We have what's known as the additive identity. The additive identity is 0, because if I add this to any number, the result is the original. 3 plus 0 equals 3. 0 plus 7 equals 7. So if I add the identity to any number, I get the number itself. And with multiplication, we have the same idea. The multiplicative identity is 1 because if I do 3 times 1, I end up with the same number. And if I do 1 times 7, I end up with the same number. So it's the identity because you end up as yourself. So 3 times 1 gives you 3, 1 times 7 gives you 7. We also have inverses. An additive inverse is any number such that if you add the original to, so if you add a number, sorry, let me start again. The additive inverse is a number such that if you add it to the original, the sum will give you 0. That's 0 is known as the additive identity. So the additive inverse of 4 is negative 4 because 4 plus negative 4 gives you 0, the additive identity. And we have the same thing for multiplication. The multiplicative inverse is a number such that if you multiply the original number by the inverse, you get 1, where 1 was the multiplicative identity. So if I ask the question, what is the multiplicative inverse of 4? You're asking yourself, okay, well, let's see, 4 times what number is equal to 1? And we know that as 1/4. It's also the reciprocal, the flipped fraction, 4 over 1, multiplied by 1 over 4 equals 1. So the multiplicative inverse of 4 is 1/4 because when I multiply the two together, I get the multiplicative identity. The multiplicative identity is 1. So let's a little review on some basic vocabulary. Now coming over here, let's talk about the matrix vocabulary. We have the additive identity for matrices, which is all zeros, because if I add this to any 2 by 2 matrix, I'm going to get the sum, which is the same as the original, just like we did in the previous page, additive identity. The multiplicative identity we talked about just a couple pages ago is 1, 0, 0, 1. 1's on the diagonals, 0's everywhere else, because when you multiply a 2 by 2 matrix by this, the product is going to be the same as the original. Now we get to the additive inverse. We did this a couple days ago. Any matrix such that when added to the original matrix yields a sum of all zeros, known as the identity matrix. All right, we're talking about that one up there. And then we have the multiplicative inverse. Any matrix such that when multiplied by the original matrix yields a product that equals the multiplicative identity. And the multiplicative identity that we're going to be dealing with is 2 by 2 matrices, which is 1, 0, 0, 1. Okay, so keeping that in mind, then this should be true. This should be true. A matrix multiplied by its inverse should equal the identity. Or the inverse of a matrix multiplied by the original should equal the identity. So suppose matrix A has a multiplicative inverse, and we're going to call that A to the negative 1, which is also known as A inverse. A inverse. So if I want to determine whether A and B are inverses, here's matrix A, here's matrix B. Here's the question I'm asking. Is A times B equal to I, where I is the identity? So multiply A times B and see if it equals I. I will wait. So here I multiplied matrix A by matrix B. Here's my work in over here. And now I see that when I simplify things, I get 1, 0, 0, 1, which is known as the identity matrix. We also need to check it the other way around, though. So I do need to multiply B times A and see if it gives me the identity matrix as well. Take a minute and decide whether or not B times A is equal to I also. Put me on pause and do matrix B times matrix A. Okay, welcome back. B times A does equal 1, 0, 0, 1. Therefore, we would say that matrix A and matrix B are multiplicative inverses in terms of matrices. So if I actually wanted to learn how to calculate the inverse of a 2 by 2 matrix, if it exists, we use the following theorem. If we have matrix A, which is made up of a 2 by 2 matrix, A, B, C, D, and the determinant of A doesn't equal 0, because notice down here we're dividing by the determinant of A and we can't divide by 0. So as long as the determinant is not equal to 0, then we have A inverse is equal to 1 over the determinant multiplied by what I call the flippy-flop matrix. Flippy-flop matrix. The A and the D switch locations. The B and the C become opposite signs. So this is something you're going to want to memorize how to do. So A inverse is equal to 1 over the determinant multiplied by the flippy-flop matrix. Where the flippy-flop matrix, you switch the locations of the first and the fourth, and you change the signs of the second and the third. And so if the as long as the determinant is not 0, the inverse will exist. So when I come down here and I give you matrix A and I ask you to find A inverse if it exists, well, it's a multi-step process. First thing I want to do is find the determinant of A, and as long as that's not 0, then I can go ahead and find the inverse. Let's see how that looks. I'm going to do my work while it's on pause so I can save some time. Okay, I found the determinant to be 6 minus 4 is 2. So to find the inverse, I do 1 over the determinant, which was going to become a scalar multiplication, multiplied by the flippy-flop matrix. Switched the 2 and the 3, made the 1 and the 4 negatives, and now I perform the scalar multiplication 1/2 times 2, 1/2 times negative 1, 1/2 times negative 4, and 1/2 times 3. This is my inverse matrix. If I multiplied A times A inverse, I would get, boom, 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 the identity matrix, 1, 0, 0, 1. All right, in conclusion, to determine whether two matrices are inverses of each other, multiply them together to see if you get the identity. And to find the inverse of a 2 by 2 matrix by hand, use the theorem, right here, as long as the determinant doesn't equal 0. In class tomorrow, we will work on assignment number 4. All right, looks like I'm exactly at 15 minutes. We'll see you in class tomorrow.